Science lovers and Renaissance fusion followers, welcome to this live show, Destination Stellarator. I'm Claudio Rosmino. I'll be your host for this exciting event, broadcasted right from the technological heart of our company. We are standing inside one of the laboratories, and just behind me you can see one of the stars of our R&D program. Its name is Skyfall Hot, and we will have the chance to know it better very soon. But first, let me remind you that today is totally live. We are sharing the first result from a series of experiments on the levitation of hot liquid metal in a circular melting chamber using HTS magnets and electrical current. Just think about that this experiment brings together two of our technological pillars, flowing liquid metal walls and complex superconducting magnet fields. So today I won't be alone on stage. You'll soon meet some of the beautiful minds behind the Renaissance fusion. Scientists, researchers, physicists, engineers, you name it. Men and women from 24 countries gathered here near Grenoble, France, united by a single mission. Now, let's take a look at our Destination Stellarator show. In just a few minutes, we will present a short documentary about the making of our two ambitious experiments. Then we will talk with some of our researchers and managers to reveal how we are moving closer to building a Stellarator fusion reactor. In the final part, we will have a Q&A session. We have already received some questions over the past few days, but you can still send yours during this live stream via our LinkedIn page, Instagram profile, or YouTube channel. So now it's my pleasure to introduce our first two guests, Nathaniel Becker, head of the Liquid Metal Department, and Victor Prost, Deputy Head of the Magnet and Cryogenics Department. Welcome, Nathaniel. Victor, thank you for joining us. So before we watch the documentary that shows your work over the past few weeks and months, let's briefly explain to our viewers the concept behind the Renaissance fusion reactor.
You want to start? Okay. So it consists of a Stellarator power plant, which is covered. The inside wall of it is covered in liquid metal. We want to use this liquid metal for three different things. First, heat extraction, which is, of course, important to produce electricity. We want to use it as a neutron breeder to breed the fuel, the neutron tritium breeder, sorry, to breed the fuel for the Stellarator, and also as a neutron protection barrier to protect the machine from damage and hopefully to have a longer lifetime.
Some more description?
So yes, and in order to have this liquid metal flow inside the reactor and protect the solid walls, we need the liquid metal to cover the first solid shell, and this is done leveraging the magnetic field inside the Stellarator, and we use that magnetic field to push the liquid metal onto the wall and leave the spot for the plasma, but still have a thick flowing liquid metal wall facing the plasma to do the free function that Nathaniel did. And so this experiment here is showcasing that we can do this with a background magnetic field, with thick flowing and hot liquid metals. And so this is our first time integrating two core technologies of Renaissance fusion, HTS magnets, along with thick flowing liquid metals.
So what is amazing is that here we have the spokesperson of the two main experiments that will be combined. So can you give us more details about your work and the work of your team?
Okay. So the role of the liquid metal team is to build the liquid metal loop. So everything from the pre-concepts done by the numerical team, from material selection by the material scientist, all the way to the actual design of the loop that you can see behind us, to its final fabrication, integration, and now operation.
So that was the liquid water department. Now we are going to know better the magnetic and cryogenics department.
So yes, on the magnetics and cryogenics department, we build the HTS magnets that provides the background field for the experiment, but also all the cooling system to have the HTS magnet operate at minus 250 Celsius. And one last thing was that we were also in charge of the insulation between the hot liquid metal loop as well as our cold magnets. So making that insulation within a couple of millimeters to maximize the field that we apply onto the liquid mold loop.
Okay, thank you very much, Nathaniel. Stay here with us because now we have something that we mentioned just earlier. It's a film, a documentary that will tell you a story. We have the pleasure to propose you a short but beautiful documentary showing the effort of these teams to deliver the first useful result in relation to the levitation of a liquid metal within a strong magnetic field. Let's watch it.
The idea of this demonstrator is to prove that we can suspend liquid metals thanks to electromagnetic forces. Those electromagnetic forces they will exist in the final Stellarator, so we want to be able to deal with them. We have this very unique technology that we want to spearhead at Renaissance Fusion, which is using liquid metals directly inside the chamber to first of all, extract the heat coming from the plasma, but also we want to use it as a tritium breeding blanket, so to produce the fuel needed for the fusion directly inside this liquid metal, and also to protect the inside of the reactor, so all the solid parts, from neutron bombardment, which are the main reason for material activation and degradation of those machines.
First start the experiment by melting the tin. As tin is molten, we apply pressure to the tin tank. We transfer the liquid tin to the experiment and then turn on the pump. As the pump is turned on, it starts circulating liquid metal in our experimental loop and injects it in chamber with two high velocity, high flow rate jets. They're hot in temperature. We plan to heat them up to 850 degrees, and they will be in presence of strong magnetic and electric field.
What we've done so far is we've demonstrated the pumping, so the sizing of this pump, which we've made ourselves, works. So we know that we can pump the metal at flow rates and pressures that will allow us to do our experiments. We've also demonstrated that we can heat and melt the tin and transfer it to the main vessel.
Right now, we believe it's at 0.52.
Yep. Looking at the manual voltage here. So the main challenges in this experiment are the fact that we're circulating very hot liquid metal up to 150 Celsius, along with magnets that are cold down to minus 250 Celsius. So we have very hot liquid metal along with very cold magnets very close by, and we need to insulate well, but also have heating and cooling efficiently in the magnet. The second main challenge is reaching high magnetic field force.
I guess stop.
So for our future Stellarator, this experiment is of utmost importance because it showcases the integration of our technologies and allows us to build a reactor that is more compact, which means more compact means higher heat flux. And so we can deal with the increased heat flux with liquid metal walls, but we need to sustain them with high flow magnets.
Hex key there and see if it's tightened.
So for us, it's a big relief because we've been working on this experiment for almost a year and a half. And so going from the drawing board to the CAD design and then starting assembly. And so this is a culmination of a year and a half of work. And so we're all extremely proud of ourselves and excited to see the experiments and the real thing in action.
Welcome back to our live show from Renaissance Fusion Laboratory near Grenoble in France. As you can see, I now have some guests on stage, members of the teams working the liquid metal and the magnet and cryogenics department. I also have the great pleasure in welcoming the founder and current CTO of Renaissance Fusion, Francesco Volpe. So guys, first of all, we are going to introduce all of you.
Hi, my name is Luana.
Masoud.
James.
I'm Sebastian.
Nicolas.
Jack.
Victor.
Nathaniel, Ruben,
Ryan is here.
George.
Pauline.
Thank you very much. So we will have now a nice debate about your work here. And first of all, I want to start with Francesco. Let's start by exploring how these two experiments we just seen are progressing and what perspectives are emerging from them.
Yeah, the experiments are progressing very well. We, as of now, have a flow of liquid metal flowing at 600 degrees Celsius in the presence of a magnetic field of 0.5 Tesla generated by Helmholtz coils built by this team behind me. We are learning a lot of details of operation of these devices. It takes a lot of ingenuity, but also a lot of tricks in the know-how, the little operational procedures. We are learning a lot on that. This is all useful experience that will be deployed one day in the reactor of Renaissance Fusion, as well as in other reactors from other fusion manufacturers, because some of the technologies we are working on are versatile, agnostic. Any fusion reactor fusing deuterium and tritium will produce neutrons, will produce a lot of heat, and we will need to deal with these conditions. So indeed, we are learning a lot. We are very happy.
So another question is, what's the main challenges? Because you are kind of exploring an unknown territory. You are defining the law of physics somehow. So at the human level, even before the scientists, what are the main challenges?
Yeah, there are challenges ranging from physics, engineering, material science. The physics itself is very complex and multifaceted. There is a fluid in the presence of a strong magnetic field exposed to electrical currents, to thermal gradients. Eventually, we're exposed to neutron bombardments. We are in the presence of radiation. So multifaceted physics, we are learning how to put all of this together. I will mention just one example. These hot liquid metals can be corrosive, but we learned how to minimize corrosion by a proper choice of materials. So this is one of several challenges ahead. One by one, we are checking all the boxes.
So now we are in front of a machine which is working. So can you explain what is happening right now and what is going to happen in the next few weeks, months?
Yes. Right now, with the cylindrical pump that you see in our back, slightly inclined, we are pushing liquid metal upward, up some pipes called the Scorpion. They are injected, as of now you can see an image
We see on the screen, yeah.
You can see the experiment, this cylindrical chamber. So the liquid metal is injected at the top of this chamber, which is magnetized. So there are two magnets, the big cylinders, the big annuli that you see in the ring. This is one of our amazing scientists, Ruben, who was fixing a light and a camera in front of the experiment. After the liquid metal flows in the presence of the strong field and of the electrical current, it is collected at the bottom of the machine and recirculated by the pump that I described, which is called annular linear induction pump, or ALIP. We are one of only 2 or 3 organizations in the world able to build it, especially at these temperatures, which are fusion relevant.
So a complex question maybe, because these days all of you went through difficult times because it was very, very challenging to set up the second part of the experiment. But step by step, we are approaching the destination, at least the first destination. And so what's the main challenge now about the second part of the experiment, and what you think to do to move forward?
Yeah, about this particular experiment, the next challenge, or the next step, I will call it step, is to go higher and higher in temperature. Right now, it's at 600 Celsius. We need to go to 850, the same temperature as in the reactor.
I can confirm it's very hot. Yeah.
It's very hot. We can, yeah. We are at the foot of the, Vercors Massif near Grenoble, so mountains, etc., fresh weather, and yet I am in t-shirt and a jacket. The steps also are in the stronger and stronger magnetic field. Today we are at 0.5 Tesla. Eventually we will gradually approach the 10 Tesla as needed in the reactor. And there are challenges of integration. So bringing together the liquid metal technology, the HTS technology, the HTS tapes that we are using today are commercially available, but in parallel with this device, we are developing our own machines to produce our own HTS, because we have a unique approach. You can see an image right now, in fact. This is a foil, in this image, a foil of copper that has been engraved by a laser, and it allows us to de-risk this idea of building complex three-dimensional Stellarator coils in a revolutionary, simpler manner, which is indeed with foils, in this case of copper, in the future of HTS, which are engraved and simply wrapped around a cylinder. This will dramatically simplify, you can see in this image, the stack of materials, the most important one being REPCO, the superconductor in black. We are depositing all of them in-house. We are learning how to do that first on a small scale and soon in a large scale, large foils, again, to make magnets for the Stellarator. So the most important challenge of all will be integrating all of this. We'll be integrating the liquid metal as it is flowing right now behind us, with HTS magnets made with our technology, and generating accurately a Stellarator field. We will do this in one module initially, one portion of the donut, and eventually replicate these modules and assemble a full reactor.
Okay, let me ask you a general question about fusion energy now. What can make the difference in the race to the realization of a real fusion reactor?
Yeah, the difference, we want to make a difference when it concerns to extracting the heat and making the device more compact. Whatever device, not necessarily or not only our Stellarator, also a tokamak or a laser fusion device. Fusion reactors will have to be compact, will have to be cost effective, will have to be competitive with solar. This can only be achieved if they are small enough. Small enough for the same amount of power means a lot of heat, a lot of energy is being deposited on smaller surfaces. These surfaces also will be exposed to high fluxes of neutrons. So thanks to the liquid metals, we can withstand these huge fluxes of heat and neutrons as encountered only in space reentry vehicles or at the nozzle of rockets. And thanks to our HTS, we can make the reactor simpler. So this is another important aspect on the destination Stellarator, and especially commercial Stellarator or commercial fusion. It must have an acceptable size and acceptable cost. These two technologies, liquid metal and HTS, enable just that.
So now I have a question for one of you. I would like to know what's your feeling in fighting, in working every day hardly to build something that it doesn't exist on Earth, like a little star on Earth.
I mean, for sure, it's very exciting. I mean, of course, it's tiresome as well. There's like a lot of work to be done in several fronts. As Victor said, it's the combination of over a year and a half of work. Also, if you want, that's Jack was the designer of the machine. But I think everybody is very proud of the results we got so far and the next steps that are scheduled.
I would say this has been a fascinating experience. Going day to day, you're solving extremely difficult physics problems, and then the very next day, you're fighting 2 bolts that are stripped into a surface that you can't extract. So it's really exciting challenges every day, but just super interesting, super exciting stuff.
One more.
I can go. Well, as a mechanical engineer, it was a big challenge, but a real pleasure to work in the design, manufacturing, and assembling of this big magnet, this huge magnet, I would say, and the cryostat, and having accomplished this result with the machine working and doing the experiment that we were waiting for since a long time ago. It was really exciting.
Okay, I would like to send a message, for example, if there are students that are following our lives, because you were a student, maybe some of you were a student just a few years ago. What's the feeling of a student that now is doing this job?
Proudness, I would say, because it's a super interesting experiment. Being an engineer, the mechanics behind this is quite complex. So I would say to them, keep going, keep working.
So what's amazing in this job?
Sorry, what was the question again?
What is amazing in this job?
Well, I think it's one of the most ambitious projects I've ever worked on, and I think it's really very, very exciting. We're going from the design work in the office and then running across to the lab and trying things out, and it's really extremely rewarding to work in a great team with great people, and to be able to build into this sort of machine that we have behind us.
So we didn't forget that now we have the new head of the magnetic cryogenic department. So you, Ruben, just arrived here. So you have a big responsibility for the future.
Yes, I do. Well, thank you very much, Claudio. It really is a privilege to work at Renaissance Fusion. As you might imagine, the challenges facing us are simply enormous, heading towards building the Stellarator. But today really is a successful step towards that final goal. And really it is the culmination of great teamwork within the company, and the folks you see standing behind me here, as well as others not on camera, really have worked very, very hard towards this amazing step today. So very, very pleased to be here. It's only my 5th week, but really I see a great future ahead. Thank you.
Okay, thank you very much. Rainis, one word from you. So you are the one who is approaching the machine every day. So what's your feeling with this machine? Sometimes it's a bit difficult to deal with it.
So I love to work here because we work on one of the biggest liquid metal experiments that exist in the world. So that's the first thing. And secondly, the colleagues around here are super competent and great, and just a very nice place to be around, to work with them every day.
Okay, thank you very much. I think it was a very interesting debate, and I think and I hope that our followers have learned a bit more about Renaissance fusion, our activity in the fusion field, and especially the important experiment we are conducting. Let's take now a short break, 30 seconds, and we will back for our Q&A session. Welcome back to our Q&A session with Francesco, and then maybe we will have also a breaking news to share with you. So, first of all, we have some questions here. Our audience sent questions in the last few days, but I think we answered some of them. So maybe we can start from maybe what metal did you use, the liquid metal? And will it be the same in the next steps?
Yes, we use tin. In a previous experiments, we used an alloy of gallium, indium, and tin, gallium, which is used in your thermometers at home because they don't use mercury anymore. That was liquid at room temperature. Now we're using tin. You see some images now of tin before being molten. Tin is a nice metal to start working with, to start messing around and to start melting. It's an intermediate step towards lithium, which will be our next experiment, and eventually a solution of lithium hydride containing pebbles with lead on their inside. This is the ultimate material for the fusion reactor. We are approaching that step by step. So this step was tin. It was the first. It is important because it was the first hot liquid metal, as you just saw, temperatures of the order of 600 Celsius and higher.
So a lot of questions about liquid metal. For example, then we have what's the major challenge in moving from liquid tin to liquid lithium?
Yes, liquid lithium is flammable, explosive. So there are some safety aspects to consider, which will be dealt with by means of an argon inert atmosphere and by some preemptive and reactive control systems for safety. Other differences between tin and lithium is that lithium is very light, and this changes the dynamics compared to tin, but for the most part in an easy way, in a good way, because the metal will be lighter. It will be also easier to control. It will be easier to maintain this flow all around the plasma.
Okay, very technical question. My compliment to our audience. Why do you think liquid metal is the best option for neutron shielding?
Yes, liquid metal in our approach can face the plasma directly, and therefore is the best approach for shielding neutrons, because the neutrons will be slowed down and absorbed immediately before they reach any solid material and before they damage it or activate it. Other organizations, both public and private, also use liquid metals, but behind solid walls. That's the main difference, which means the neutrons first have to cross these solid walls, and they damage them, they render them radioactive, which has implications for maintenance, for frequent replacement of parts. So the key differentiator here is liquid metals directly exposed to the plasma.
Okay, you mentioned damage, and there is a question about, have you observed the corrosion issues during the experiment?
We have observed corrosion. not tissues. It's under control. We identified materials that can withstand less than 1 micron of corrosion per day. So this translates to 1 millimeter every 3 years, tolerable in a reactor. So, but yes, we do observe corrosion.
One more question about the fission plant. Why not use sodium as in the case in nuclear fission plants?
Yeah, sodium can be used to extract heat. Is not particularly efficient in decelerating the neutrons, in attenuating them. And most importantly, sodium doesn't breed the tritium. So lithium is really the only material that fulfills all the 3 requirements that we are after.
Okay, we arrived at the end of the list of questions sent by our audience. So thank you very much first. But now, before leaving, we have something to reveal, to unveil.
Yes, so there is some excitement in the control room just next to us. Because we have evidence that the liquid metal is responding to the currents applied and to the magnetic field applied. So the hot liquid metal flow is deflecting, and so it's a very encouraging sign. We are getting one step closer to destination Stellarator. We are very excited. So we did it before at room temperature. This is the first time we do under reactor relevant high temperature conditions. So. Congratulations to the team that is working so hard in the control room. I'm very excited to announce this breaking news.
Congratulations. It was a really nice gift for us, for our live streaming show, and also for our followers. Thank you very much, Francesco, for your interesting answers. And as we have reached the end of our time, we promise to respond directly to the other questions after the show. I'd like to thank everyone who took part and contributed to this event, especially the Bazai technical crew, Claire, Lionel, I forget someone else, I'm sorry, and the whole team who managed the live stream. A personal thanks also to my teammate, Chloe and Lucille, for their work, support, and patience during the last weeks. It was a pleasure being here with you, and of course a huge thanks to you all. You can rewatch the Destination Stellarator on our YouTube channel. Stay tuned with us through our website, Instagram, and LinkedIn. Thank you very much, and see you soon.